We're going to be looking at 2.3, solving radical equations graphically. So in my first example, I'm actually not going to solve them graphically, which means generally graphically can be means manually by graph, but often it means using technology or something of this sort. Um, so we're going to determine the roots of the square root of x minus 1 minus 2 is equal to 0. Now, I just want to draw your attention to sort of three scenarios. Here, if I start off with the square root of x plus 1. Now, often what we choose to do with radical equations is we tend to square both sides. Now, why do we do that? So that we can get rid of this radical. Because the square root squared, now these two are inverse operations and they cancel each other out. So really all that we're left with is x plus 1 here, which was our radicand. So I would like to call this behaves like a monomial, right, as you're squaring it. So now let's take a look at scenario number 2. When the coefficient in front of a radical or a square root, and then we square both sides, right? So let's say I'm going to square that. Well, what happens? Really, we square the coefficient and we square the radical as well. We end up with 16 x plus, times x plus 1, close brackets, and we can multiply that out to have 16x plus 16. Now, the reason why that might be the case, now I'm just going to borrow some of this space over here, because we have 4 times the square root of x plus 1 times, now if we square it, that's 4 times the square root of x plus 1. And as we multiply these two quantities together, we can split it up, since it's 4 times that, we can split it up into 4 times 4 times the square root of x plus 1 times the square root of x plus 1. And that is just simply 4 squared, and then the square root of x plus 1 times itself can be expressed as the square root of x plus 1 squared. So that's the second scenario, really. Now, I know that you're quite familiar with this, but example number 3. Now, what do we normally do? I like to think, now let's look what's different from here. The coefficient here, we may or may not have 1. Sure, it's 1. We have a radicand, but then outside of the radical is a plus 2, is the constant. So if I want to try to get rid of the radical, I'm just going to square. And if I square this expression, there we did, I squared it. What does it mean? It means the square root of x plus 1 plus 2 times the square root of x plus 1 plus 2. Now this gets a little bit nasty, simply because we have to FOIL this out. So if you notice that there's a radical plus a constant, and that constant's outside the radical, really, you're going to have to treat it like a binomial. Anyways, I'm sure you're familiar with this. If not, make sure you ask questions. So let us get started. Let us begin with the first example here. So example number 1, we're going to determine the roots of the square root of x minus 1 minus 2. And we're going to solve, or is equal to 0. Is equal to 0 because it's an equation. We're going to solve it algebraically. Now, my first step really is I'm going to just rewrite the question in my own language here, in my own handwriting. I find that's really helpful when I'm solving an algebraic equation. Now, I know that eventually what would I like to do when I'm solving a radical equation? I always like to isolate my radical, then do the inverse. So here, this is my radical. This is my radical right here. So I'm going to try to get that over to one side. The easiest way to do that would be to add 2 to both sides. So here is x minus 1 is equal to 2. So I really added 2 to both sides. And then the next thing I'm going to do, so that's an equation. So an equation, I kept it in balance because I did the same operation to both sides. The next thing that I'm going to do, here's x minus 1 is equal to 2. The next thing I'm going to choose to do is I'm going to square both sides. Now this keeps the equality of the equation because I'm doing it to both sides. Now what I'm doing here is I'm actually annotating on the left-hand side. So the benefit of doing this in your work, it demonstrates, if you're highly confident in your work, it demonstrates that you have a lot of knowledge. But also, when it comes back to reviewing the material on your own and you've annotated a lot of your work, it really helps you study and it helps you get back into your head or how you solved this at once. Anyways, let's get back to the equation. So I'm going to square the left-hand side. The square root of x minus 1 squared is really just x minus 1. 2 squared is 4. Well, I certainly hope this works out here. I'm kind of feeling nervous. So now I just simply have to check this. So x minus 1 is equal to 4. This implies that a possible solution, now I'm going to call it possible because it's not for sure, possible solution is x is equal to 5. If I add 1 to both sides, I get x is equal to 5. Now, what I have to do with radicals, now you may want to say you must check with radicals. And maybe we'll get back to that a little bit later. So now I must check, so I'm going to have to plug this back in. So the square root of x minus 1, we think that x is 5. 5 minus 1, subtract 2, is that equal to 0? So the square root of 4 minus 2 is equal to 0. So 2 minus 2 is equal to 0, so 0 is equal to 0. Check. So this is no longer a possible solution. I'm just going to say, therefore, solution at x is equal to, now I'm going to put this in set brackets because that's the most correct way of doing that. Putting in set brackets is very important. Here you're saying the solution is x is the number 5. They'll often get you, this is actually incorrect because you're saying that the solution is a horizontal line, right? Or sorry, a vertical line where x is 5. No, that's not what you're trying to say. You're not trying to say your solution is a vertical line. You're trying to say it's a number. Anyways, let me get back to where we're going here. I'll pick a nice color. Oh, everybody likes green. Hope that's not too light. So what is an extraneous root? Extraneous root is probably best described as a false root or a false solution. Now, why do we get a false solution in algebra? Rarely does algebra fall off the rails, but sometimes we incorporate mistakes in our reasoning, and we have to be very conscious of that. And here we did. So, and the mistake, now we are willing to acknowledge this mistake. The mistake comes in at this part right here when you square. So for instance, let's just give you an example. I'm going to give you an example of what a extraneous solution is, or what has an extraneous solution. For instance, the square root of x is equal to -1. We know that there does not exist a real number x such that the square root will be negative number. By definition, when we take the square root, the principal root it's always positive. But yet, if we jump into the algebra, I can just quickly find the solution. There's my original equation, right? The square root of x squared is x. -1 squared is 1. So if I just jump in the algebra, I get, hey, there's a solution here where x is equal to 1. And clearly, the square root of x does not equal to negative 1. The square root of 1 does not equal to negative 1, right? Simply because if the root sign is already written for us, it's assumed to be positive. All right, so there we have it. Now, here's a weird thing. Why did we place a restriction? Oh my God, I got so excited doing the math, I forgot. One thing that we can do here is, why did we place a restriction? If you notice, I didn't put a restriction on here. None of my work has a restriction. However, I should note that x minus 1 should be greater than or equal to 0. In other words, my radicand has to be 0 or positive. This leads us, if I add 1 to both sides, that my restriction should have been x is greater than or equal to 1. So why did I place a restriction here? It's to eliminate extraneous roots. Now, I don't think that I would prefer that you guys check your solutions, but also please place a restriction on your solutions as well.